Hello friends, welcome back to the channel. In today's video, we are going to learn how to package a Helm chart, upload it to JFrog Artifactory Helm repository, and then use that package to deploy an application on a Kubernetes cluster. So if you are working with Kubernetes, OpenShift, DevOps or CI/CD pipelines, this is a very common workflow that you will come across in real-world projects. Before we jump into the hands-on demonstration, let's just spend a few minutes understanding the basics. Well, what is JFrog Artifactory? As many of you may already know, JFrog Artifactory is a universal artifact repository manager. In simple terms, it is a centralized platform where organizations store, manage, secure, and distribute build dependencies as well as build output artifacts. One of the biggest advantages of JFrog Artifactory is its integration capabilities. It integrates seamlessly with a wide range of tools and platforms such as Docker, Helm, Maven, Gradle, NPM, Jenkins, GitHub Actions, cloud platforms, and many other third-party products. Because of this, Artifactory often becomes a central component in enterprise CI/CD pipelines. Now let's understand what a Helm package is and why it is widely used in Kubernetes environments. Well, Helm is a package manager for Kubernetes. It enables us to define, install, upgrade, and manage Kubernetes applications using reusable templates called Helm charts. So instead of manually modifying multiple Kubernetes manifest files with hard-coded values, Helm allows us to use variables, conditionals, loops, and other powerful templating features to dynamically generate the required Kubernetes manifest. Using a central values.yaml file, we can provide application-specific configurations such as image versions, replica counts, environment variables, resource limits, secret references, and many other settings. We can also maintain separate values files for different environments such as dev environment, SIT, UAT, and production environment, making deployments more consistent, standardized, and easier to manage. Another major advantage of Helm is that it packages all Kubernetes resources required by an application into a single deployable unit called a Helm chart. This simplifies application deployment, upgrades, rollbacks, and version management across Kubernetes and OpenShift clusters. One of the features I personally like most about Helm is its release management capability. Whenever we deploy an application using Helm, Helm creates and tracks a release for that deployment. Because Helm maintains release history, we can easily upgrade applications, view deployment history, compare revisions, and roll back to previous versions if something goes wrong. So, instead of manually applying dozens of Kubernetes manifest files one by one using kubectl apply commands, Helm manages everything as a single logical unit. This significantly simplifies Kubernetes application lifecycle management and makes deployments more reliable and repeatable. Now that we have a basic understanding of Helm and a JFrog Artifactory, let's move on to creating a Helm chart, packaging it, uploading to JFrog Artifactory, and finally deploying it to Kubernetes cluster. Now let's start with the Helm installation. I have already installed Helm on my Windows machine, but I will walk you through the complete installation process step by step. To install Helm on Windows, first visit the official Helm installation documentation, that is helm.sh/docs/intro/install. On this page, scroll down to from the binary releases section. Every Helm release provides binary packages for multiple operating systems, including Windows, Linux, and Mac OS. These binaries can be downloaded and installed manually. Here, click on desired version, and from the list of available releases, download the latest Windows AMD 64 package. I have already downloaded, so I will cancel it. Once the download is complete, extract the zip file and copy it to a convenient location. For example, I have copied inside E drive tools. Now open the extracted folder. Inside Helm version 4.2.0 Windows AMD 64, you will find another folder named Windows AMD 64. Open that folder and you will see helm.exe. Copy this complete path Next, we need to add this location to the Windows path environment variable so that Helm can be executed from any command prompt. To do that, search for environment variables. Here under System Properties Advanced, you will find environment variables. Click on this. Under User Variables for admin, select Path and click on Edit. And here you will need to click on New. Since I have already added it, so you will be able to see the path is available here. Click on OK. Click OK to save all the changes. Once the changes are saved, either restart your machine or open a new command prompt or a PowerShell window. Now let's verify the installation. In my Visual Studio IDE terminal, if I run Helm version command, if the installation is successful, you should see the output similar to this. Here we can see version 4.2.0 is available. Now that Helm is installed, let's move on to creating our first Helm chart and understanding its structure. Let's create a Helm chart for one of our Spring Boot applications. This is very similar to the approach followed in many real-world organizations, where application deployment manifests are packaged and managed using Helm charts. Here in Visual Studio Code, I have the source code of my SEH students Spring Boot microservice available under eDrive study code repo directory. At the root of this application, we already have files such as Docker file, Jenkins file, and other project related files. This is also where we will create our Helm chart. To generate a new Helm chart, we will run Helm create and then Helm chart name. We are giving it manifest build. As soon as we execute this command, Helm automatically generates the basic chart structure for us. So here you will see creating manifest build, and under manifest build, we can see a default Helm chart structure. All these files and directories are created automatically by Helm. Think of this as a starter template or boilerplate structure that provides everything required to begin building a Helm chart. Let's quickly understand what each component is used for. Let's start with chart.yaml. This chart.yaml contains metadata about the Helm chart such as chart name, version of chart, description, and other details. And this values.yaml contains the default configuration values that will be injected into our Kubernetes manifest during deployment. And this charts directory is used for storing dependent charts if our application relies on other Helm charts. This templates directory is most important directory because it contains the Kubernetes resource templates that Helm renders during deployment. Helm has already generated several commonly used Kubernetes manifests for us. For example, deployment.yaml defines the Kubernetes deployment resource. Service.yaml defines the service used to expose the application. The same way, ingress.yaml contains the ingress configuration. HPA.yaml is used for horizontal pod auto scaling. Service account.yaml creates a service account if required. _helpers.tpl contains reusable template functions and helper definitions that can be referenced across multiple templates. Here notes.txt displays useful information after a successful Helm installation. In real-world projects, we typically customize these files according to our application's requirements. We can also create additional templates as needed, such as persistent volume and persistent volume claims manifest, config maps, secrets, role and role bindings, network policies, routes for OpenShift, any other Kubernetes resources required by the application. For now, we will keep the default structure as it is and gradually customize it as we move forward. Now, in real-world organization, we usually maintain separate values files for different environments such as dev, SIT, UAT, and production. This allows us to keep environment-specific configurations separate while using the same Helm chart across all environments. For example, we can create directories like SCH-INSIT, dev, UAT, production. Here SCH is my project, IN stands for India. You can follow your organization's standard. Inside each directory, we will maintain a dedicated values file. Now, instead of manually copying the values file multiple times, we can use simple bash for loop. Let me quickly explain what's happening here. The loop iterates through 4 values. Those are SIT, dev, UAT and prod. During each iteration, the variable env gets assigned one of these values. This cp command copies original values.yaml file. The destination path is dynamically generated using the current value of env. Hit enter. Now let's update one of the values files. I will use values schsit.yaml as an example. If you open the file, you will notice the following configuration. Replica count 1. This means Kubernetes will create a single pod or one running instance of this Spring Boot microservice. Next, we need to configure the Docker image details. Since we are storing our container images in JFrog Artifactory, let's retrieve the image repository information from there. Well, I am using a trial version of JFrog Artifactory for this demonstration. Navigate to platform and then artifacts. Under SCH Docker repository, you will find the SCH students image repository containing the Docker image for our Spring Boot microservice. Here, click on Set Me Up in the top right corner and select the Docker pull command. You will see a repository URL. Copy this and paste it here under repository. Here, append the repository name as well, and under tag, if I expand this, copy the tag name. Here, repository specifies where Kubernetes should pull the image from. Pull policy, if not present, tells Kubernetes to pull the image only if it is not already available on the node. Tag specifies the exact image version that should be deployed. Now let's quickly understand the chart.yaml file. By default, Helm generates something similar to this. The most important fields are API version, indicates the Helm chart API version being used. Name, the name of Helm chart, typically this should match our application name. Description, a brief description of the chart. Type application specifies that this chart deploys an application. Helm also supports library charts. Then version, the version of the Helm chart itself. This should be updated whenever chart changes are made. Then app version, this represents the version of application being deployed. This is informational and helps identify which application version the chart is associated with. Since our application name is SCH students, let's update the chart name accordingly. And app version, from pom.xml, let's copy the version number and update it here. Let's remove these commented sections. So our final chart.yaml will look like this. Now that our Helm chart is ready, let's create a Helm repository in JFrog Artifactory where we will store and manage our Helm packages. Here in my JFrog Artifactory instance, navigate to administration and then repositories, and from here create a repository and select pre-built setup. Then choose Helm from here. For the repository prefix, I will use SCH since this is my project name. Once you click create, Artifactory automatically creates two repositories. One is SEH Helm local and SEH Helm. Let's quickly understand the purpose of these repositories. As we already know, a local repository is used to store artifacts physically inside Artifactory. In our case, all Helm packages that we upload will be stored in SEH Helm local. But why do we need a virtual repository? A virtual repository acts as a single access point that can aggregate one or more repositories behind the scenes. Instead of developers, CI/CD pipelines, and the deployment tools accessing multiple repositories directly, they can connect to a single virtual repository. Click on Continue from here. Here, set up a Helm client, generate token. You will need to provide the password and click on Generate token and create instructions. So here you will get this access token. Copy this and save it somewhere. Also this Helm repo add command. Click on Done from here. So here we can see SEH Helm and SEH Helm local repositories are available. Now let's package our Helm chart using Helm package and then chart name. To create a deployable Helm package, we will need to run this command. What does this command do? When Helm executes this command, it reads chart.yaml, collects all templates and the chart files, packages everything into a compressed archive and generate a .tgz file. For example, since our chart YAML contains name as SEH students and the chart version is 010, so Helm will generate SEH students -010.tgz file. Let's run the command and see. Successfully packaged chart and saved it to SEH students -010.tgz. As you can see, Helm successfully created the package. Now let's upload this package to JFrog Artifactory and we will use curl command here. Let me explain this command. Here curl is used to upload files over HTTP. -u provides the JFrog username and access token for authentication. -t specifies the file to upload, that is sh-students-010.tgz, and the URL specifies the target repository and the path where the package will be stored. In this example, the package will be uploaded into the folder structure inside SEH Helm local, then SEH students, and then release/100 inside Artifactory. Hit enter. After executing this command, you will receive a response similar to this one. This response confirms that the package was successfully uploaded. Artifactory stored it in the SEH Helm local repository. Checksums were generated for integrity verification. A download URL was created for future access. Now let's verify the upload. For that, in the JFrog Artifactory, navigate to Platform, Artifacts, SEH Helm. Remember, we are browsing the virtual repository here because the virtual repository exposes content from the underlying local repository. We can see our uploaded package even though it was physically stored in SEH Helm local. So if we browse to SEH students and then release, then 100, this TGZ file is available inside SEH Helm, that is a virtual repository. Also here in SEH Helm local, SEH students, release 100, and then SEH students 100 TGZ. Inside SEH students, all the chart.yaml templates, all the files are available here. So we can see that our Helm package has been uploaded successfully and is now available for deployment. At this point, our Helm chart has been packaged, versioned and stored in JFrog Artifactory, making it ready for consumption by deployment pipelines and Kubernetes clusters. Now let's see how to use Helm to perform deployments on a Kubernetes or OpenShift cluster. Let me switch over to my Kubernetes master node in MobaXterm. First, let's verify the cluster using kubectl get nodes command. As you can see, I have a Kubernetes cluster consisting of one master node, also called as control plane node, and two worker nodes. I'm already inside /opt/code repo directory. This is where I will download the Helm package that we uploaded earlier to JFrog Artifactory. Well, there are multiple ways to retrieve a Helm chart from Artifactory. In real projects, teams commonly use Helm repository commands such as Helm repo add, Helm repo update, and Helm pull. However, it's also perfectly fine to download the package directly using a curl command. For this demonstration, I will use curl. Here, we are using the username and access token that we generated earlier in JFrog Artifactory. And -o option tells curl to download the file and save it using its original file name. Hit enter. Once the download completes, we can verify it using ls-lart. As you can see, the Helm package students-010.tgz has been downloaded successfully. Now, for this demonstration, I will extract the chart package so that I can access the environment specific values files packaged inside it. For that, tar-xgf and then tgz file name. Hit enter. Now move into the chart directory cd and sh students. Here we can see the chart files, templates, and the environment specific values files. Now let's deploy the application using Helm upgrade --install command. Let me explain this command because it is one of the most commonly used Helm commands in real world deployments. Here we are using Helm upgrade. This updates an existing release, and --install tells Helm to install the application if the release does not exist. sh students is the Helm release name. Dot represents the current Helm chart directory. -f then this values file name tells Helm to use the SIT environment configuration. -n this is the namespace, specifies the Kubernetes namespace where the application will be deployed. Well, one of the biggest advantages of using Helm upgrade --install is that the command is idempotent, means we can run the same command repeatedly. If the application is not already deployed, Helm performs an installation. If the application already exists, Helm performs an upgrade. That's exactly why most CI/CD pipelines use Helm upgrade --install instead of maintaining separate install and upgrade commands. Hit enter. So after running the command, Helm returns release, then release name has been upgraded, happy helming. You will also see details such as release name, namespace, deployment status, revision number, and some helpful post deployment commands. So here, status deployed and revision 4. This means Helm has successfully created or updated the Kubernetes resources and is now tracking revision 4 of this release. One of the major advantages of Helm is that every deployment revision is recorded, allowing us to perform rollbacks whenever required. Here you can see revision as 4 because I have done the deployment again for testing purpose. Now let's validate whether Kubernetes has started creating the resource using kubectl get pods and then name. Here we can see the deployment sh students has been successfully created and the Kubernetes is actively trying to bring the pod up. However, the pod is getting restarted, which means the container is repeatedly starting and then crashing. So Kubernetes keeps restarting it. Now let's inspect the root cause by checking the pod logs. kubectl logs -f and then pod name. Now here is the real issue. The application is trying to connect to MySQL, but it is not receiving the actual values for DB hostname and a DB port. Instead, it is literally receiving the placeholders. So what's happening here? These values are supposed to come from config map or environment variables injected into the pod, but they are not being resolved properly. As a result, the MySQL JDBC driver fails to pass the connection string and the application crashes during startup. This is why the pod goes into crash loop backoff. Now I'm not going to spend too much time fixing this here because that part belongs to the Kubernetes config map and environment variable injection topic, which I have already covered separately. The goal of this video is different. We are focusing on how to package Helm charts and push them into JFrog Artifactory and then deploy them on a Kubernetes cluster. So now let's move on and check the Helm releases using Helm list -n /sitin. So this command shows all Helm releases deployed in a specific namespace. Now pay attention to the revision here for SEH students. Every time we perform a Helm upgrade, Helm does not overwrite the previous deployment. Instead, it creates a new revision and stores the full history of that release. This gives us powerful release management capabilities. For example, we can view full deployment history, compare different revisions, audit what changed between releases, and most importantly, roll back to a previous stable version if something goes wrong. This is one of the biggest advantages of Helm in Kubernetes and OpenShift environments. With just a single tool, we can install, upgrade, manage, and roll back complex applications in a controlled and versioned way. And that brings us to the end of the session. In upcoming videos, I will show how real enterprise deployments are done using Helm, Kubernetes, OpenShift, Jenkins pipelines, JFrog Artifactory, and Git-based CI/CD workflows. If you found this video helpful, make sure to like, share, and subscribe to the channel. Thanks for watching, and as always, happy learning.